Welcome everybody, welcome to Reactions of Alkyl Halides. We've been going through the series SN2, E2, SN1, and the last one is E1. There are lots of other reactions like Suzuki coupling and so many other different reactions that alkyl halides can do. We're just going to touch on the surface here and go because of the time limitations. So let's look at what we can do with a tertiary alkyl halide in a protic environment. We saw this before, didn't we? Tertiary and protic? Yes, we did. We saw it in SN1. Well, we are going to focus really on the side product of SN1, which is E1, with alkyl halides. If you want just pure E1 and no SN1, or if you want major E1 with very little SN1, then try alcohols, and we'll do that too. But if you have a really good leaving group like this, in a weak nucleophile, weak base, which is in this case is a solvent also, you're not really going to go that far. You're just going to get a mixture of substitution, nucleophilic unimolecular, and elimination unimolecular. Let's see how this happens. Let's go. So as you can see, if you take the alkyl halide, drop a line to that carbon, there are no hydrogens on it. Therefore, it's tertiary. We wouldn't deliberately take a primary or a secondary and try to do this E1 or SN1 reaction because that gives us so many side products. It's really not worth your time. Okay, it's not practical. But if you have a tertiary, yeah, things can go. Why? Let's see why. Let's take this and mix it up with some water. Let's say you have this in a bottle. It's going to stay in the bottle. It's not going to ionize and go anywhere. But the minute you put a ionizing or a very high dielectric constant solvent, which can ionize polar bonds, then that's when things start to happen. If you take this bond here, the bromine's electronegative, electron withdrawing, and carbon's really more on the electropositive side. So carbon's going to give electrons toward the bromine, and so this is a polarized bond. And also the overlap between carbon and bromine is not that great because bromine's huge, carbon's small, so really they don't overlap as well. So it is a weak bond which can be rattled and broken. And that's what the water's trying to do. The water here has got lone pairs, it's got all that extra electrons that can go somewhere and do things, and so why not? So water is looking for something that's electron deficient. And in this entire molecule, the alkyl groups, are really water repellent. They're going to whack that water out. However, that carbon's got a slight delta positive. And the bromine is delta minus. So polar loves polar. Like dissolves like. Water surrounds it. And before you know it, water is trying to nudge that bromine out. And so after some time, bromine really can't take it anymore. It leaves with the electrons, of course. So you get an alkyl carbocation. Carbocation doesn't have octets, and we said, you don't ever violate the octet rule. But in this case, since it's tertiary, you have 3 friends here donating along sigma bonds. That's plus inductive effect. Plus, you have all these carbons and hydrogens that can get parallel to this p orbital and donate electron density. Let's say you have the carbon or the hydrogen come in. It can, go in and do hyperconjugation. Same here, whenever these hydrogens get parallel to this p orbital, they can go in and donate. There are 2 here. So all of these, when they align with that p orbital parallelly, these sigma bonds can donate electron density into that empty orbital. So it loves it. It's got lots of friends helping out, and it's just in a happy place. Well, the oxygen comes in and tries to also help out by donating those lone pair electrons in here and doing a ion dipole interaction. You can have about 6 of these. So all of these water molecules also try to stabilize it. So therefore, tertiary carbocations can live a very short life, very, very short life, but you can still see them with spectroscopy. So here is your intermediate. What's next? Is it going to just stay there? It's still very high energy. You still don't have an octet there. So therefore, you can never rest in peace in this state. You need to have an octet-filled carbon. So therefore, what's going to happen is, one, this water molecule can, bam, attack that, and then you'll get SN1. Or sometimes it can pull off that hydrogen that's parallel to this. It's in hyperconjugation here, and these electrons are kind of stretching over into this, and the water molecule can pull off that hydrogen. Now it's got choices. It can pull this off, these off, or these off. When you have a double bond that's forming, then carbon-carbon bonds that can donate electron density into it would make it really stable and lower its energy. So this is where you will have 1, 2, 3, 4 carbon-carbon bonds surrounding that tetra-substituted alkene. Can't get better than that. So therefore, the water somehow knows that, and it's going to take that hydrogen out. And those hydrogen electrons, which are like smearing over to do hyperconjugation, just go, bam, fall flat on that p orbital. And so now you're going to have those electrons come down and fill up that p orbital. One of them's going to be here. So you'll get a pi bond. All elimination reactions are meant for forming pi bonds, all of them, no exception. So therefore, you are going to get a double bond right here between the carbons that have the most number of substituents. Here, you don't have to rotate and get anti-periplanar and all of that. You just pull off the hydrogen that's going to make the most stable product. So it's always Zaitsev. There's no question of, is it Hofmann, is it Zaitsev, what size is the base? Base is teeny always, it's protoic solvent. Even if you have a big base, you're already doing it from the carbocation, not the initial starting material. So therefore, this is always going to give you the Zaitsev product. Now, having said all of that, I want to mention that E1 is still your minor product. This is your E1. What's your major? It's just the water molecule, boom, falling on the p orbital, which you know can happen a lot faster. Major is going to be water molecule falling head-on on that p orbital and giving you, after deprotonation, an alcohol. Is this the only product that can form? Do you have something else that can form? Let's say SN1 major. In addition to this minor product, you can have others too by pulling this off and this off. So here again, you don't have to draw a Newman projection to see which ones are aligned and so on. In this case, you can either pull off this hydrogen or this hydrogen. So let's call this 1, 2, 3. So H2 and H2 prime, let's say. If you pull off one of these that's aligned here and where your methyl's facing the isopropyl, that would give you a cis or a Z. Or if you pull off the hydrogen where when the methyl group is pointing away from the isopropyl, you'll get an E. So there are two options there. And you can have a Z or an E. Because if you cut this in two, this is high priority and this is high priority. High priority groups on opposite side is going to be your E. So this is your E alkene. Minor, and it is an E alkene. If you pull off the hydrogen when you have the methyl facing the isopropyl, then you're going to get a Z alkene. This is again another minor. These are going to be a lot less than your SN1. So this would be more than this would be more than this, and this would be more than pulling off any one of these identical hydrogens over here. So that is going to give you a di-substituted alkene. This is tri and this is tetra. So this is going to be E1 minor, and that's going to be di. This is tri, and this is tetra. And Zaitsev rule says tetra would be more than tri, and tri would be more than di. And that's always true. It's always going to be Zaitsev for E1. So I'm going to put Zaitsev rules. Let's look at another possibility for these reactions. Here's a secondary. Do secondaries undergo E1? They'll be really, really very slow, except if you have pi bonds on adjacent carbons. Well, what can they do? You know, pi bonds are good at running around and doing resonance. So that's really when secondary and primary become significant in E1 and SN1. Whatever affects the stability of the intermediate is going to affect SN1 and E1 because it's the same intermediate for both, for E1 and SN1. So here too, same thing. Let's say we have this and we have a protic solvent. Let's say I have methanol. It's not as great as water because water is about 80 dielectric constant. This is about 30, so it's a lot slower. However, it can happen. Methanol's got a lone pair here. This is a polarized bond, and chlorine's electronegative. This bond's really not being held too well with that carbon. With the halogen carbon bond is really polarized and stretched thin, so it can be easily rattled to give you a carbocation. What's so special about it? Let's look at this carbocation here. It's got a positive right here, and right next door is a huge party going on. You got these pi bonds running around in circles, chasing each other. Well, the positive charge wants to get in on the action. It pulls out that pi bond. And now you got a pi bond stuck over there, which means these guys aren't having as much fun anymore. Well, they're trying. These can go up and give you a double bond right here. Well, it looks like the positive is moving, but you know all along is the electrons that are running around. The positive charge is just showing you where the electrons have left that carbon. These are going to just like swing open like a gate and slam dunk on that positive, that p orbital. That's pretty much what happens during resonance. And so you have positive is here. And again, this is going to be really the most stable form. It's going to be here most of the time in this conformation where you have a benzene ring and they can run around. The party is only disrupted, you know, once in a while. So here's your positive. Once it's up here, then you can get attacked with your nucleophile and get SN1, which is going to be your major. And I'm going to draw that out every time. And this can then pull off a hydrogen. There are no hydrogens here, so it's got to pull off the terminal hydrogen there. And always it's the lone pair that does all of the work. You may have 20 carbons here. They're not going to do a thing. They're greasy, you know, lazy stuff. But this lone pair is really active and takes those electrons and just dunks it inside that MTP. Now you have a pi bond there. And that's typically what happens in an E1. So back again, you have this octet for your carbon, and you got a pi. So always the product of an E, whether it's E1 or E2, is an alkene. This is minor. Major again, and here we really don't have cis and trans and tri and di. There's only one possibility. There's only one methyl group here. It's not branched. And you can have major SN1. You can hike up the amount of E1 by increasing the temperature, upping that temperature, but you're still going to get a huge amount of SN1 even at high temperatures, okay? If you heat it way too much, then it's just all going to evaporate and distill out, you see? So there's a limit. Let's look at that. It's got all these spikes coming out. What's going on here? Let's say we take this and we heat it up with another protic solvent. Let's say we heat it up with ethanol. We like this watery, neutral, high solvents. All right, let's take this. And here's your iodide. Iodide's got the same problem here as these guys. It's huge. In this case, it's not really very electronegative, but the overlap's really weak. And iodide's kind of more electronegative than carbon, not as electronegative as chlorine or bromine, but you know, it can still handle a negative charge really nicely. So again, same story, polar solvent. This polar and this polar get along really well until it sees the positive charge here, electrophilic center here, and it kind of hones in on there and then kind of rattles this bond and it leaves, can't take it anymore. Too much interference. So here's your iodine that's going to leave and leave with a hole in the heart of this molecule. And here is the iodide with all of the lone pairs. It's got an octet and it's also solvalized with the ethanol. And your ethanol is going to always be hanging out with these carbocations. Carbocations need electron density, and this is like the sorority sisters. They hold hands, come over here, bring him cookies and cakes, and before you know it, he's zapped. He's gone. So you can pull off a hydrogen, but well, look at this. That's where you would pull it off, but there's no hydrogen there. And it's looking at that and saying, I'm secondary. No, secondary is not that great. I don't want second place. But if I pull that over here, I'll get a tertiary. Tertiaries are always more stable. So rearrangements are very common. So whenever these carbon-carbon bonds get parallel to that p orbital, they kind of wrap house, take those sigma electrons, roll over, and you are going to get a tertiary carbocation here. Well, what happens to all these ethanols? Well, they kind of vacate this carbocation, go on to the next one right next door, and so these kind of go away, and then you'll have other ethanol molecules come over, and now you have all of these holding hands. Support system here to this guy who's kind of got a broken heart. The iodide's run away with all his money and house and sports car and everything that he had. Support sorority group here, and they come in, well, catch him and give you SN1. That's pretty much it for major product. And some of them are really going to go run away with a neighbor. So they look at this carbon, and this carbon, kind of similar situation to here. This is the guy with more money, so it runs off with this guy. So here's your hydrogen here, and the lone pair, whenever this hydrogen's kind of donating electrons to this positive, zaps him right there. And so those electrons go over here and form a pi bond. That's got a lot of friends. Tetra-substituted. So that would be your minor, but it would be the most amount of the minor. So I would say minor 1, E1. This is SN1, and that's always your major. Sometimes SN1's like 80%, E1's like 20%, or anywhere between. Sometimes it could be 60-40, but usually SN1's more. Well, what else can we do? Well, this guy's got a friend here, and it's got people, hydrogens over here that's willing to come down and kind of ease that pain. So the ethanol can pull off this hydrogen or this hydrogen. This one's at least got another friend here and here, so it's tri-substituted. So you could get a double bond right there. And that would be less like this, and that is going to be an E. So minor 2 E1. This is E in terms of cis and trans geometric isomerism. Well, any other possibilities? Well, that's a beta, and here's a beta. And so that hydrogen can just drop those electrons onto that carbocation, and you can have a di-substituted. So this is tetra, and they're all E1, tetra tri, and tri-E, and this is tri-Z, and this is di. Typically, Zaitsev products would fall into a gradation like this, going tetra to tri to di, major to minor. So this might be like a % or two. These might be a little bit more, but you would get most amount of the tetra. So these are all minor, but within the minor, you would have more of this and this and this. So these are all minor E1. All right, let's look at some other fun stuff to do. What happened with the iodide? Well, the iodide is just going to leave here, and that's just going to be solvated, and it's just going to get washed down the sink. Okay, solvated iodide. So alkyl halides are a really good source of starting materials to make nucleophilic substitutions and eliminations. But if you want to do an elimination 1, E1, you wouldn't really waste a very hard to get or nice starting material. You get a whole bunch of mixtures which you have to separate all day, all night, on the bench. It's very wasteful to do that. But if you take these alcohols, they're kind of cheap, dime a dozen. You can buy them, they're extracted from plant material, a lot of them, and it's really easy to make by taking alkanes, oxidizing them with oxygen. It just hardly costs anything. Well, that's not true if you look at the catalog, but it's a lot cheaper than getting like fancy alkyl halides. So if you take these alcohols, these, in the presence of sulfuric acid, give you mainly E1. So here you can say major E1. So here, if you take sulfuric acid here, sulfuric acid, has got a sulfur. It's really electron withdrawing. It's going to put all those electrons here. So this is basically a proton floating around. And so that hydrogen is going to be zapped by this nucleophilic oxygen, which then pushes those electrons over to give you a very nice protonated species. In this reaction, you're going to start your reaction with a protonated alcohol. We saw earlier, we don't have the pKa chart here today, but in the pKa chart, you can see that a water molecule that's protonated has a pK of around -2. That's an excellent leaving group. This is just kind of revving to go because when it leaves, it's be water, one of the most stable molecules on the planet. So this is literally now our starting point. So we take this, and this is going to roll up those electrons and leave as water. And that's really what we were kind of looking for. But once you pull those electrons off, remember there's a hydrogen, it's going to leave a gaping hole here. So that you have a hydrogen, and then you'll have a p orbital going in and out of there, and just going to draw it like that. There's a positive charge waiting for somebody. So what else is here? Sulfuric acid typically comes with a small amount of water. There'll be at least a small amount of water. It's very hygroscopic. And so the water molecule can then attack this again. Same story as before. They don't attack like a strong nucleophile. they kind of pull around, wait for this alkane to become more and more vulnerable to attack, and, well, and he's not looking, he's zapped. Okay. Now, in this case, if you put your water molecule back, you'll go back to your starting material. It's not another product. But if you pull off a hydrogen, well, there are hydrogens beta here and beta here. What about this hydrogen? What about pulling off that hydrogen? You're going to get a minus here. But wait, the minus and the plus are going to be in different orbitals. It's going to be like a carbene. We don't want carbenes. They're like really high energy. However, if you pull off these hydrogens, they're okay. So that's the whole deal with sulfuric acid and water, because water, if it attacks the carbocation, will go back to your starting material. No fuss over there. I mean, then you're going to start all over and come over here again. Now you can do something different, and that is take these lone pairs and pull off a beta hydrogen. And so in this case, this is a secondary, but even the neighbors are secondary. So we're just not going to do a rearrangement. We're just going to go with this product because they do have some numbers for what percentages of products we form. And this is going to be 75%. Well, I expected more, but it's 75%. That's what the literature says. Well, what's the 25%? Well, if you look at this, these are opposite directions, so they're E. Whenever you have an E, you also have a likelihood of forming a Z, which is like that, where both the groups that are coming off of the pi bond are on the same side. The high priority groups, hydrogens, low priority groups are on the same side, but we usually look at these, methyl and ethyl, on the same side, same side Z, and that's 25%. Well, over here, we talked about this hydrogen being pulled off of the sulfuric acid, so you're going to get HSO4 minus coming off. Well, what about this? Isn't this another oxygen? And besides, it's not just an oxygen, it's an oxygen minus, so isn't it going to be even more nucleophilic than this oxygen lone pair? And you got three of them, you got, muscles here, so you got muscle strength here to attack. Why are we doing that? Well, if you look really closely at this, these electrons are all tied up here in resonance. And so they're not really interested in attacking that carbocation and forming a very unstable carbon sulfate bond. Okay, so it's basically thermodynamics. You form an unstable product, which is high energy, then you're going to go back and form the more stable product. This is your thermodynamic sink. So this is a bad nucleophile, okay, or poor nucleophile. Let's take this molecule. I changed it out because it was very similar to a previous example. So let's do something different. Let's look at this guy over here. Here's a nice 5-membered ring. You have an alcohol, then they heat it up in water and sulfuric acid. Basically, really very acidic media. And see what they got. They got cyclohexene. Now, how did that happen? I mean, there was nothing with a 6-membered ring here. And here you have a 6-membered ring staring at you. What happened? Well, let's look at it. Let's see what are the possibilities for this molecule. Can it ever go there? Let's do the same mechanism we did here. Well, you're going to have the lone pair zap that proton and give off a sulfate. So you're going to get a 5-membered ring, and you have an oxygen here that's now revving to leave. It's got that extra hydrogen. Now it knows even if it leaves here, it's be fine. It's going to be a water molecule. It doesn't really need this molecule anymore. So it pulls and tugs and pulls, and in the meanwhile, these water molecules kind of surround it and help it kick out that water, because alkyl groups don't like protonated species in there. They're very greasy, and these guys are very polar, ionic, and so they don't get along. After much tugging and pulling, they decide to separate, go their own ways, get their own condos, be out there on their own, doing their own stuff. So here's your positive here. Molecules are doing it way before people. Now you have choices. You can have water attack. Well, you're going to go back here. No fun in that. You're already there. I mean, you already didn't like it there. That's why you left. So why would you go back there? Even if you do go back, you're going to do this again, right? So why repeat the same mistakes? So now this is primary. Should we even form it? It's very, very transient. That means it's just not going to be there for more than a microsecond. As soon as it forms, these guys are going to walk in there because it's just too terrible to be primary and be divorced. It's just too much. So now that goes over there and expands that ring, and I'm just going to draw it out like this first. Now you took electrons out of that carbon, so the carbon here is positive. Now you can go in here and say, well, this is just a 6-membered ring. I'm just drawing it kind of crazy. So now you got this positive here. You got your empty orbital here. Now you can do stuff. Now you kind of a little bit more relaxed. You're still secondary. It's not that great. But if you take off your neighbor's hydrogens, pull out those guys there with some water molecule here, then you're going to be all set. You're going to pull that hydrogen off. Those electrons are going to just go bam onto the empty orbital. It is already doing hyperconjugation. All it just goes, sleeps right on top of that, that sigma. So you get a pi bond, and that's what you have here. That's your major product. So you can have rearrangement by hydrogens moving over. We saw plenty of that. R groups moving over, especially methyl groups moving over. You can have rearrangement by ring expansion to go to a more stable ring. It's very unlikely if you had a 6-membered ring with an alcohol, you go back to a 5. No, because 6 is, more stable. We drew all those chairs like a zillion times to show you why they were more stable. So you pretty much like to be here. You're not going to go back there. That's why it's the major. Do you have any other products here? You could have an alkene here by taking off that. You could have other stuff happen. This hydrogen move over and give you a positive here. And that's another very likely product. And so then that positive can then have a pi bond forming anywhere here. So those are the major products there. This would be more than this. All right, so kind of a brief review. If you have a tertiary alkyl halide or alcohol, you could pull off the leaving group. And again, leaving group is key here to this mechanism. Because if you look at this first step, you're going to have to wrench that bond and pull it out. That's the hardest thing to do, break that bond. So that's going to be your bottleneck. If only you can get here, then you can go plain sailing after that, but you've got to go over that hill. So that's your slow step. And slow steps are your rate determining steps. So for your rate equation, you would do the experiment by increasing the amount, measuring the rate. You would increase the water, measure the rate, and see which one's really getting into that rate expression. And they found out the nucleophile, whatever it is, didn't affect the rate at all. It was always the alkyl halide. Why? Because for it to separate out, it has to do it all by itself. It has to think about all the things that happened to it, feel sorry for itself, and go through this whole psyched up, emotional upheaval before it breaks up. Once it breaks up, it's quite fine. But until then, you need a lot of energy to get there. And even then, you're very unstable. So your rate is going to be K alkyl halide, Rx. So there are two things in here, R and X. It's not just like R. So where R is concerned, our tertiary is much, much, much faster than secondary. And this kind of thing is not even going to happen on a primary. Okay, unless with major rearrangement. So tertiary is going to be your fastest, always. Whereas X is concerned, X is going to be the exact same as for all of the others. So X is the leaving group. Lower the pK of the conjugate acid, better the leaving group. Okay, same thing that we saw with all of the others. Lower the pKa of the HX, better the leaving group ability of X. This is going to be the same for all four because in all of them the rate expression has got Rx, R and X. All right, what else is different? When you take this reaction, you're always going to get a multi-step reaction. You have to form this, then you have to form this. If it is an SN1, then you have another extra step of deprotonation. So this is always going to be multi-step. And since you have only one molecule in the rate expression, experimentally, when they double this, this would double. When they triple this, this would triple. When they triple the water, nothing happens. So this is an experimentally obtained rate. Okay, you can't really cook this up looking at the reaction. You have to do the experiment. So if we found it, order is 1, therefore it's unimolecular. That's key. Multi-step. Well, if you look at this, alkyl halides, the first step is going to be the most difficult thing to do. So that's going to be a very high activation energy, and you're still not done. You're still going to go to that R plus here. Then you can do your E1, SN1. E1, higher energy, but more stable product. So this is going to be your alkene, E1. You can do a SN1, which is going to be your major. So that's going to go to your protonated form, and then you would have deprotonation. So what's on the mountaintop here? Well, the mountaintop is bromine coming off. So whenever you have a mountaintop, you have a transition state where your X is actually getting stretched before it gets dumped. So this is your intermediate, and we always do your rate for getting to this step, because that's the slow step, because your activation energy is huge. The activation energies for the second step is actually a lot smaller. So once you've gone over this, the weak base, which is also a nucleophile, taking off that hydrogen is going to be really fast, which is why it's really not in the rate expression. And if your nucleophile, if your water acts as a nucleophile, you're going to zap that R plus and get ROH2. The activation energy for that will be even lower. And then deprotonating that is just like a quick and easy step. So that's even lower. So that's why when you heat this up, because the activation energy to go back here is lower than for this, alcohols tend to go back and then come back as alkenes. So if you keep heating this up over and over time, these kind of go back here to this intermediate step and then come back as alkenes, and you get more and more alkenes. This is your thermodynamic sink. We're talking about thermodynamics. This is some energy here. I mean, you could even say for this part delta G. This is your reaction profile or reaction coordinate. So as time goes, Rx is just going to come over here, and then with your nucleophile or weak base form substitution SN1 or elimination E1. Now what happens if you have an alcohol? Do you do the same thing? Is the first step the slowest one always? In this case, picking up the proton, it's just like picking up something from the street. It's really easy to do. Just bam, gets on there, and now you have this protonated form. This is the hard thing to do, wrenching out that water molecule, because here's your sigma bond. You got to break that. It's not easy. It takes all of your energy. So here, the alkyl group tries to get rid of the water with protonation, but it's still got to, pay. So this leaves, then now you got to intermediate this. So for this reaction, for the alcohols, let me put for ROH here. The first step is a small step, and then the second one is the heart-wrenching one. Then you form a high-energy carbocation. Then you're going to have to pull those beta hydrogens out to get your alkene. So here's your ROH2 intermediate. And then this is your highest activation energy among all of these. Therefore, this is your rate determining step. It's going from this to an R plus. And, well, your water molecule comes off. This then going to the alkene is a little easier. You just have to pull off those beta hydrogens. That's key. In all cases, forming the double bond is your final product for E1 reactions. Again, as I said, at typical reaction conditions, E1 is minor, SN1 is major. You really have to hike up the temperature and be able to do that, without evaporating all your solvents, etc., in order to do E1 major. If you want E1 major, try sulfuric acid. All right. So this is just a little blip on E1 reactions. Let's compare E1 and E2 here. See how they're different. Up to now, every single thing's different between elimination 1 and elimination 2. Elimination 2 has to have a base come in, pull off the hydrogen, make the pi bond, and kick off the leaving group all at once. So you need the base there. Bimolecular. Rate depends on the base pulling off that hydrogen. So there's got to be two molecules there, the Rx and the base. This is a similarity here. Now put that over here. R group being tertiary is an advantage here because you'll get a more substituted alkene. But it can also happen on secondary and primary, whereas here it's mainly tertiary. Leaving group ability is the same for all four of them. They're always in the rate expression, and therefore leaving group having a lower pKa for the HX is going to make that a better leaving group. So this is also the same. Leaving group has a lower pKa that would correspond to a higher reaction rate. Okay, this is multi-step. Here it all happens bam, wham in one step. So this is going to be one step. This is non-concerted, this is concerted. I mean, that's pretty much the definition of one step. Everything happens simultaneously. What else? If you take the graph, obviously it's going to reflect that. You're going to have a lot of steps here on the graph. Whereas here you're just going to have just one step. I'm just drawing a very rough sketch here. We kind of have to look at this. And even here you'll have the same potential energy or energy and reaction coordinate. What else? Here, water, alcohol, these are your weak bases. Sometimes, like triethylamine, these are your weak bases. So base is weak. Base is weak. If base is strong, well, even if it's tertiary, primary, or secondary, it's going to do E2. Base is strong. pKa above 11. usually above 15. Over here, because you have a carbocation, if it's not really stable, then you can rearrange. Here it's all happening at the same time. There's no carbocation for people to be hopping around. It's just one shot done. So this has got rearrangements, which is really not a good thing when you think about it, because then you're going to get a whole slew of products. Here you have no rearrangements. Okay, what else? Product is an alkene. Product is an alkene. That's a similarity. Okay, products are alkene. Another thing is here you need to have a certain angle, like 180 degrees between the leaving group. So you need to have an anti-periplanar orientation. That's not the case here, because the leaving group's already gone. You just have to form that pi bond with the beta hydrogen. So over here, anti-periplanarity is maintained in transition state. Anti-periplanarity configuration is not needed. So if you look at this, in an E1, you already have a flat carbocation, and then you have a hydrogen just giving off electrons and forming a pi bond. So you really have always Zaitsev. Because this anti-periplanar configuration is not having to constrain it in certain angles and positions. So therefore you have Zaitsev always. Over here, because of this anti-periplanarity and the size of the base is important, steric is important. So stereochemistry, stereo and regiochemistry affected by anti-periplanar arrangement, configuration, and by steric. Therefore, you get Hofmann elimination, you get sometimes E over Z or Z over E, and so you can get Zaitsev and Hofmann. When you do an E2, you have a very strong base, and so E2 is the major, and SN2 is the minor. But they're competing. Whereas over here, when you do this reaction, typically E1 is the minor, and SN1 is your major. One other similarity here is temperature would hike up the amount of product of elimination in both reactions, because you have lots of side products when you have elimination, so your delta S goes up, and that actually increases the minus delta G. So therefore you're going to get thermodynamically more elimination product as temperature goes up. So temperature increases E. Here too, temperature increases E2 over SN2 if they're competing reactions. As we said before, here we like to have protic solvents because those can actually stabilize this, ionize this, and also get deprotonated and form a product. Whereas with E2 and SN2, you want to use aprotic, and we saw all the data that we had in those charts in our previous videos, where protic solvents were really slowing down SN2 and E2. Aprotic was really the one that stabilizes the transition states of SN2 and E2 and makes them faster. So that's actually a big difference. So aprotic solvents make E2 and SN2 faster, which is why if you want to do more E2 rather than SN2 in primary and secondary, we use protic. You are forming a carbocation, and therefore protic solvents increase the rate of E1 and SN1, both. One other thing is, well, if you have acids, that also makes the protic solvent even more polar and ionic, and so therefore acids accelerate E1. Well, a couple more things. Over here we said that the base is not in the rate expression, so we could say in E1, base does not affect rate. In E2, it's just the opposite. Base is in the rate expression. Stronger the base, better and faster the reaction. It's in the rate expression. One thing that's common, I put these common ones in pink here. One thing that's really common is that E1 and E2 will not occur on a bridgehead for ring size 7 and smaller. That's Brett's rule. E1 and E2 do not occur on bridgeheads in small rings, okay? So what I mean is if you have a leaving group like this, the leaving group bring on the bridgehead, not here or here because those can form alkenes like this, but if it is here or here, you cannot form an alkene there. No E1, E2, because that angle is not there for it to overlap. But if this ring had been more than 7 carbons, is bigger, then it can kind of nudge its way and form a double bond over there, and the angle would be fine. So this is just a blip on what E1 reactions are, how do they happen, what's the best starting materials to use, what's the difference between E1 and E2. All right, we've done our series. Let's do some examples. Let's do some wheels. See where your fortune lies. Talk to you soon, guys, and bye.